Welcome to my course on Advanced Mathematical Physics. This is the 9th lecture of this series, and over the past few lectures we have been discussing vectors. We have seen that in differential geometry there are typically three distinct ways, but equivalent ways of talking about vectors. Today we are going to talk about the geometer's definition of the vector. But before that, let me remind you of the other two definitions that we have already talked about. One, not so much in great detail in this course, but this I assume is familiar to most physicists. The physicist definition sees a vector as a bunch of n numbers, if you are talking of n-dimensional vectors, that transform in a particular manner under a change of coordinates. On the other hand, the algebraists version is quite close to the geometric picture of tangents to curves, but it uses the tangents to curves to finally define vectors in a coordinate-independent way as a linear derivation map from C infinity M to R. I will not say anything more about this except at the very end, simply because we have spent quite a long time discussing this particular view of vectors over the past few lectures. But what we have seen is that the collection of all tangent vectors at a point P form a n-dimensional linear vector space which we have called TPM, the tangent plane at the point P to the manifold M. Today we are going to take a look at what vectors look like from a geometer's point of view, where curves whose tangents we are talking about take center stage. We have, in fact, talked extensively about the intuition behind this definition at the very beginning of our discourse on vectors in the 6th lecture of this series. So if what I'm going to talk about now seems a bit too abstract to you, I would suggest that you go back to that lecture. If you do that, you will see that many of the things that I am saying here, though abstract sounding, is backed rather strongly by standard geometric intuition. In the geometric viewpoint, tangent vectors are tied directly to curves, or rather to equivalence classes of curves. So let me first describe to you what this notion of equivalence class really means here. For this, we start with a CK manifold. Of course, we will usually be using C infinity manifolds more often than not in physics, but CK manifolds are enough to describe what tangent vectors really mean, where K is some finite integer, and let P be a point in the manifold M. We are describing equivalence classes between curves on the manifold, and to begin with that, we have to define what exactly is this equivalence relation. So here, let gamma 1 and gamma 2 be two curves of class CK, both passing through P. That means they are maps from intervals on the real line to the manifold, and the value of these maps at t equal to 0 is the point P. Now we say that gamma 1 and gamma 2 share the same tangent if, according to a chart u, phi on M, with P belonging to the domain U of this chart, we have the following. The rate at which the function phi composite gamma 1 for the first curve changes with t at t equal to 0 is the same as the rate at which phi composite gamma 2 changes with t at t equal to 0. Remember, the map phi takes a point on the manifold and maps it to a bunch of n numbers. So these functions that you see, phi composite gamma 1 and phi composite gamma 2, carry an interval of the real line on which the variable t lives to an open subset of Rn. So this equality is basically an equality between the derivatives of n functions, one for each component of phi composite gamma. Now, the moment you see a definition like this, it should raise a red flag. This definition is tied entirely to the choice of a particular chart u, phi on M. And if something really has to have a meaning in differential geometry, it should really make sense beyond just specific charts. That's one of the first lessons that differential geometry teaches us. However, this particular definition, despite appearances, is not really tied to a coordinate chart. And to see this, what we should do is take a look at some other chart, v, chi, such that P, our point in question, is actually in the intersection of u and v. And just for simplicity, just to simplify the notation for the time being, instead of looking at the whole maps phi and chi, let's look at their components. Phi of P, of course, gives you n numbers, which we call x1 of P, x2 of P, up to xn of P. That is, the xi's are the coordinates according to the chart u, phi. And x1, x2, xn are the so-called coordinate functions. Whereas chi of P can be broken up again into n components, y1 of P, y2 of P, up to yn of P. And this is basically what we usually mean when we say we have changed coordinates from the x's, x1, x2 up to xn, to the y's, y1, y2 up to yn. Now, when we are saying something like ddt of phi composite gamma 1 at t equal to 0 equals ddt of phi composite gamma 2 at t equal to 0, which is our definition of two curves sharing the same tangent, what we really are saying is for each one of I running from 1, 2 up to n, ddt of xi composite gamma 1 at t equal to 0 is ddt of xi composite gamma 2 at t equal to 0. This, of course, is the definition of gamma 1 and gamma 2 sharing a tangent according to the chart u, phi. But what about the chart v, chi? There, of course, you would have to use the coordinate functions y, i's. So the question is ddt of yi composite gamma 1 at t equal to 0 the same as ddt of yi composite gamma 2 at t equal to 0 as well? Let's see that. So ddt of yi composite gamma 1 can be written, of course, in the following manner. Yi composite gamma 1 is the same as yi composed with phi inverse composed with phi composite gamma 1. Of course, composition of functions being associative, we can actually change the bracket from phi inverse composite phi being the identity being inserted in between yi and gamma 1 to this particular form. Yi composite phi inverse composed with phi composite gamma 1, the one which we had written down. Now note, phi composite gamma 1 takes you from the interval I on which t lives to a subset of Rn, phi of u. And phi inverse followed by yi, that is yi composite phi inverse, takes you from phi of u to R, a real number. So this basically is a composition of two functions. Of course, it's a composition of four functions as it stands, but you can think of these two as specific functions, and this is really ddt of this function of phi of gamma 1 of t. Now this is, of course, set up perfectly well for use of the chain rule. And for that, what we need to do is differentiate yi composite phi inverse with respect to the xj components. So that is why the jth component, that's what I wrote down earlier also as capital dj. This is really the partial derivative the way we know it. And it has to be evaluated at phi composite gamma 1 at t equal to 0. Since gamma 1 at t equal to 0 is p, this is really at phi of p. This has to be multiplied according to the chain rule by derivative ddt of the thing that you have put in here xj composite gamma 1 at t. We are using the summation convention here, so the multiplication has to be followed up by a sum over all j. But we know, according to the definition of two curves sharing a tangent, that this quantity ddt of xj composite gamma 1 at t is the same as ddt of xj composite gamma 2 at t. At, of course, t equal to 0. So if we just replace this by the corresponding quantity containing the curve gamma 2, what we end up with is simply ddt of yi composite gamma 2 at t. And since this is true for all I running from 1 to n, ddt of chi composite gamma 1 at t equal to 0, which is just a combination of all these n ddt's of yi composite gamma 1, is the same as ddt of chi composite gamma 2 at t equal to 0. And what this implies is, if two curves share the same tangent according to any one of the charts that contain the point P, they share the same tangent according to all charts containing the point P. So this particular notion of sharing a common tangent, despite being expressed via a chart, is actually independent of charts. And so it makes broader geometric sense beyond just a particular choice of coordinates. Now, as we have been saying over and over again, what we are looking for is an equivalence relation defined on the set of all curves passing through a particular point P on the manifold. There are no prizes for guessing that this relation that we have just demonstrated is chart independent. Sharing a common tangent is exactly the equivalence relation that we have been hinting at. Now, in order to figure out that this really is an equivalence relation, what we need to do is prove the three basic properties an equivalence relation should obey. They are reflexive, symmetric, and the transitive properties. Now, the fact that sharing a common tangent is a reflexive relation is obvious. To be reflexive, gamma must share a tangent with gamma. A rather obvious and trivial thing. What about symmetric? Symmetric in this context means that if gamma 1 shares a tangent with gamma 2, then gamma 2 shares a tangent with gamma 1. Once again, that's an obvious result. Finally, we come to the transitive property, which essentially would mean that if gamma 1 shares a tangent with gamma 2 and gamma 2 in turn shares a tangent with gamma 3, then gamma 1 shares a tangent with gamma 3. Now, gamma 1 sharing a tangent with gamma 2 means that a particular quantity is the same for gamma 1 and gamma 2. There's an equality involved in the definition that we just introduced a while ago of the rate at which the function phi composite gamma changes. Now, the same thing occurs, that is, the same thing is equal between gamma 2 and gamma 3, and it's a basic property of equality that gamma 1 must have the same property as gamma 3 and so must share a tangent with it. Once again, this result is also obvious. Frankly, an equivalence relation is basically a generalization of the notion of equality. And since here we have defined the notion of sharing a tangent using the result that something is equal between gamma 1 and gamma 2, the two curves who share a tangent, it should be obvious that an equivalence relation is just what this one is. Now, once we have an equivalence relation, what we can do is use that equivalence relation to define equivalence classes. An equivalence class of a curve gamma, this gamma within a square bracket, is defined to be a set of all the curves gamma prime which share a tangent with gamma. Of course, the set includes gamma itself. Now, what equivalence classes do in general in any algebraic setting is that it partitions the set of all into pieces. In this case, it partitions the set of all curves through P into disjoint pieces. Note that every curve has to belong to one equivalence relation or the other, simply because, if nothing else, it's in its own equivalence class. And therefore, the union of all the equivalence classes will give you the set of all curves passing through the point P. And what is more important, and what this word partition actually implies, is that these sets, the subsets which are the equivalence classes, are actually either identical or disjoint. Either the equivalence class of gamma 1 is the same as the equivalence class of gamma 2, which will happen if gamma 2 happens to belong to the equivalence class of gamma 1, or gamma 1 and gamma 2 have disjoint equivalence classes with no curve in common. Now this last part is very easy to see. If there is a curve gamma which is in common between these two equivalence classes of gamma 1 and gamma 2, then gamma must share a tangent with gamma 1 and it must also share a tangent with gamma 2. Since sharing a tangent is a transitive property, this would immediately imply that gamma 1 shares a tangent with gamma 2 and therefore they must belong to the same equivalence class. And as a result, the equivalence classes would then become identical. If not disjoint, definitely identical. Now, it is precisely these equivalence classes which are the vectors in the geometer's version of the thing. These equivalence classes are also called germs. Here, germ, the word does not mean microbes, but rather it means stuff from which things grow. The same root is used here as in the word germinate. The equivalence classes can be thought of as basically the starting point from curves starting at P, which then go over to different parts of the manifold. Now, exactly why these things can be called vectors is what we are going to explore next. But first, some nomenclature. We will denote the set of all these equivalence classes by tau Pm. P here, of course, labels with a point where all the elements of these classes share a tangent. M, of course, is for the manifold. Now, you might have guessed that I really want to call this TPM, but we have already used the word TPM for the set of all linear derivative maps earlier. So, I am nominally calling this particular set tau Pm. Later on, you will see that this is exactly the same, or at least this is in one-to-one correspondence with our standard tangent plane to a manifold at the point P, TPM. Now, in order to see what kind of vector nature these equivalence classes of curves really exhibit, let us first construct a map. This map is chart dependent. Given a chart u, phi on M, the map that we will construct, we will call that f phi p, where the phi refers, of course, to the chart in question and the p to the point where these curves all share a common tangent. Now, this is a map which takes elements of tau Pm, that is equivalence classes of curves, to Rn, set of all real numbers, n real numbers. And what does it do? It maps an equivalence class gamma to the following number, the rate at which the function phi composite gamma of t changes at t equal to 0. These are precisely those numbers whose equality defined the notion of sharing a tangent for us a while ago. Now, it stands to reason that all elements of a particular equivalence class must give you the same value for this quantity. In fact, that is what defines the equivalence class for me at the first point. So, this is a well-defined map. Note that whenever we are talking about a function which acts on a collection of things, by essentially picking out one element from that collection and saying that, okay, this is the number you get out of that, you have to be careful and check whether the map is well defined. In other words, if instead of using gamma, a particular curve from this equivalence class, if you had used a different curve, say gamma prime in the same equivalence class, would you have got the same answer? Of course, the answer here is yes. That's simply because that is how you define the equivalence classes in the first place. Now, if the map f phi p were to act on two equivalence classes, one of a curve gamma and another of a curve gamma prime, and gave you the same value, then what this would tell you is that the curves gamma and the gamma prime that you used here, that you took out of their respective equivalence classes and used to evaluate this particular quantity, must share a tangent at the point P, and therefore they must belong to each other's equivalence classes, and that means the two equivalence classes must be identical. But this simply means that the map f phi p is injective. It is one-to-one. If it returns the same result from two inputs, the two inputs must be one and the same. Now, what is also very important is that in addition to being injective or one-to-one, this mapping is also onto, or in more fancy terms, surjective. Now, in order to show that, what we need to show is no matter what element you pick out of Rn, any bunch of n real numbers that you can pick from here, there will be some element of tau Pn, some equivalence classes of curves for which f phi p will return that particular set of n numbers. To see this, let us consider an arbitrary element x from Rn, and let us define a curve gamma x in this particular fashion. Gamma x is a curve, so it basically is a map which goes from an interval I containing t equal to 0 to the manifold, and you define it in this particular manner. Gamma xt is defined to be the map phi inverse acting on phi of p plus t times x. So here what you are doing is you are starting essentially from the point P, applying phi to find that element of Rn which corresponds to the coordinates of the point P, and then at t equal to 0, of course, what this map does is that it returns to you phi inverse acting on phi p, that is the point P itself. If you focus on the argument here, phi p is the coordinate of the point P, and what you are doing is you are adding to it a part which is proportional to t, and the factor, the coefficient here is x. Of course, what you are doing is you are applying phi inverse to essentially ensure that what you get at the end is from this coordinate you convert back and get a point on the manifold. So as t ranges over this interval I, gamma x of t traces out a particular curve on the manifold. At t equal to 0, this curve returns the value p. But it's also very easy to check that if we were to apply f phi p on this particular curve, or rather on that equivalence class which contains this curve, then the result is of course ddt of phi composed with gamma x acting on t. Now if you compose phi with gamma x and apply the result on t, what you get is phi p plus tx. And the derivative of that with respect to t, of course, is simply nothing but the vector x. In other words, no matter what x you choose, you can find some equivalence classes of curves, this particular equivalence class of curves, which acted upon by f phi p will return the x that you are looking for. And since x here is an arbitrary element of Rn, what this proves is f phi p is a surjective map, if you don't want to sound so pompous, an onto map. So what we have shown is f phi p is both one-to-one and onto, that is bijective, or in other words, invertible. And what is f phi p inverse? It's a map which takes you from an element of Rn to an equivalence class of curves. It takes the vector x in Rn to precisely the equivalence class of the curve gamma x, the curve that we had just constructed a while ago. The upshot of all this is that this map f phi p establishes a one-to-one correspondence between tau pm on the one hand and Rn on the other. That is, to every germ, to every equivalence class of curves, it associates a bunch of n real numbers. Now this is exactly what connects the geometer's version of a vector with the physicist's version. To see the actual connection properly, what we also need to see is what happens to this bunch of n numbers. When you change your coordinates, note that the map f phi p is tied to a particular chart u, phi. If we were to change your coordinate to say v, chi, a new chart, then you would have to, of course, recalculate the number associated with a particular curve. Let's look at what f chi p does to an equivalence class of curves, the germ gamma, and we are taking a look at the ith number or ith component of this. After all, this is going to yield an n component vector. I'm looking at the ith component of that. That, of course, is simply ddt of chi's ith component acting on gamma, which of course is what we call yi, if y1, y2, yn are the coordinate functions associated with a chart v, chi. Now, we will play the same trick that we did a while ago. We will write chi composed with gamma as chi composed with phi inverse, composed with phi, composed with gamma, and then use a chain rule. And if you use a chain rule, what you will do is take the chi composite phi inverse, which is of course the same as yi composite phi inverse. Remember, the ith component of chi is exactly what the coordinate function yi is. Carry out its jth partial derivative with respect to xj at the point given by phi composite gamma of 0, which is nothing but phi of p, and then contract that is multiply and then sum up over j with ddt of xj composite gamma and evaluate that at t equal to 0. Now, if we were to denote the ith component of f chi p of gamma, which is the element of the n-dimensional real vector space Rn corresponding to the germ gamma by capital V chi I, the chi here just tells you that these are the components that you get if you were to use a chart v, chi, then this result actually tells you v chi I is a linear combination of the v phi j's, which are nothing but the ddt of xj composite gamma at t equal to 0, sitting on the right here, and the factor in front is nothing but the jth partial derivative of yi composite phi inverse, the proxy function corresponding to the ith coordinate function according to the new chart, evaluated at phi of p. This is exactly what you denote by del yi del xj at p, and therefore the component transformation rule that we get out of the basic geometer's definition is simply the same as the one which physicists use as a defining property of vectors. If you change your coordinates, the new vector components are going to be combinations of the old vector components, and the combination factors, the coefficients, are going to essentially be partial derivatives of the new functions with respect to the old functions. Of course, del yi del xj at p, the suffix p is missing. It should be there. So we have established the vector component transformation rule. And this completely identifies the geometer's version, which is rather abstract, of an equivalence classes of curves in a one-to-one fashion with a bunch of n real numbers which transform in a particular manner, which is exactly the physicist's definition of a vector. The transformation rule here tells you that the ith component of v chi is linearly dependent on the components of V phi. If you look at the objects V chi and V phi as a whole, it's obvious that if you apply a linear transformation on V phi, you get V chi. And the matrix version of this particular linear transformation has elements made out of these partial derivatives. Now, this is something very familiar to all of us. This map, the linear map that converts V phi to V chi, is nothing but the differential map or the Jacobian map of the transition function chi composite phi inverse. Now, let me remind you that in advanced calculus, the differential of a function is not really an infinitesimal quantity. It's a linear map which transforms changes of the input into linear approximations to changes of the output. Now, because V chi and V phi are f chi p acting on gamma and f phi p acting on gamma respectively, it's easy to see that this tells us that the maps f chi p and f phi p are also related to each other via this differential or Jacobian map of the transition function chi composite phi inverse. Now, we have been calling these entities vectors, and in fact the notation V that we are using for that indicates that we are thinking of them as vectors. However, while the elements of Rn has a nice vector structure, we are yet to define a vector structure on tau pm. We need to specify how two equivalence classes of curves can be combined in a linear fashion. But it is very easy to do this by using the map f phi p or f chi p, whichever map you are using depending on which chart you are using at the moment, and exploiting the linear structure which Rn, where the V chi live, already has. And that actually helps us to prove that tau pm is an n-dimensional linear vector space. And the way to prove that would be to first make a beginning by defining how to linearly combine equivalence classes. Now, this rule for linear combination of equivalence classes that you can see here may seem a bit complicated, but it really isn't so. What it tells you is that if you want to combine the inequivalence class of the curves gamma 1 with an equivalence class of curve gamma 2 with alpha and beta as real coefficients, then what you would first do is apply f phi p to take gamma 1 to a member of Rn. And f phi p has to be applied on gamma 2, the equivalence class of gamma 2, to get another element which belongs to Rn as well. Now, these two things are elements of Rn, so they are ordinary n vectors, so they can obviously be linearly combined using the standard method. So, alpha times this entity plus beta times this entity is perfectly well defined, and this gives us an n vector. But f phi p inverse exactly does the job of converting an n vector back into an equivalence class of curves that is a member of tau pm. So, the upshot of all this is, this whole procedure allows you to first go from tau pm to Rn via application of f phi p. You linearly combine the vectors that you get there, and then you go back to tau pm using f phi p inverse. And as a result of this, we have a definition of how to linearly combine two equivalence classes of curves to give you a single equivalence class of curves. Now, this is not, of course, enough to show that this is a valid linear vector space operation. That is, under this operation, you really do have a linear vector space. You have to verify all the basic properties, the defining properties of linear vector spaces using this particular definition. The proof itself is rather tedious, but there are no surprises there. After all, the fact that these entities are elements of a well-understood vector space makes the proof rather straightforward, if a bit lengthy. Now, there's one more thing that you should really be concerned about here. You have defined a way to linearly combine two equivalence classes of curves by first going on to Rn and then coming back after doing a linear combination in Rn. While that's all very fine, note that this to and fro movement from tau pm to Rn and back uses this particular map and its inverse. And the map itself is tied down completely to a chart. So if we were to use a different chart, would you get a different result? If that happened, then of course you may not have a unique way of defining linear combination of equivalence classes of curves. But if you note that the f phi p which you use here and the f chi p that you would have to use if you were to change your chart are related by basically this simple relation. F phi p composed by the Jacobian map, a linear map, acting after that gives you f chi p. So if instead of u comma phi, if you were to use v comma chi as your chart, then here you would have f chi p sitting, but that would mean there would be, after the f chi p, there would be the Jacobian map acting on that. But you would also have to use f chi p's inverse, which will be f phi p inverse, Jacobian map's inverse, in that order. The Jacobian map inverse would actually act first, and then f chi p inverse would act. And the two Jacobian maps would essentially cancel each other out. Thus, whether you use f chi p or f phi p to define the linear combination, you end up with the same linear combination in both cases. So this particular definition of how to linearly combine two germs is actually independent of the chart, despite the fact that it looks very much like it could end up depending on it. So now that we know that tau pm is a linear vector space, Rn of course is another linear vector space of the same dimensionality, and f phi p is a one-to-one onto map between them, that is, which also, by virtue of this definition, obviously preserves linear combinations. That is, if you apply f phi p on alpha gamma 1 plus beta gamma 2, what you would get is precisely this, alpha acting on f phi p gamma 1 plus beta times f phi p gamma 2. So, basically f phi p is a linear invertible map between these two vector spaces, a vector space isomorphism. So despite the fact that the manifold itself may be a very complicated object, as long as the manifold is smooth, the tangent plane to it, TPM, is actually very, very simple. It's just Rn as far as the algebraic structure is concerned. The only thing left at this stage is to show you how the geometer's definition using germs actually ties up with the algebraic's definition of linear functionals. And the answer to that is actually very easy. We already know how to define the directional derivative of a function f, which is a smooth function, ckm function, along a curve gamma. This is something we have already used when we defined the tangent vector. The directional derivative is simply ddt of f composite gamma. That is, gamma, of course, is a map which takes you from an interval of the real line onto the manifold. F takes you from the manifold to the real line. So f composite gamma is a real interval to real line function whose derivative here is simply the ordinary derivative which you evaluate at t equal to 0. This is now the domain of ordinary first year or class 12 calculus. So given any element of tau pm, which we have called xp, this xp must be an equivalence class of curve gamma, where gamma 0, of course, has to go through p. For every xp, you can define this entity. Now, there's one problem which might immediately strike you, which is if instead of picking out gamma to represent xp, I'd taken any other curve in the equivalence class, which I could of course have done, would we have obtained the same value for the directional derivative? Or would it have depended on the particular element of this equivalence class that you pick? That the answer is the former is easy enough to see. All you have to do is follow the trick which we have played often enough. Write f composite gamma in this particular fashion and then use the chain rule, which essentially tells you that this derivative is nothing but the derivative of phi composite gamma at t, on which you apply the differential, the Jacobian map of this f composite phi inverse at the point phi p. Now, note that the part which involves a curve is just here. And if gamma tilde happens to be another curve in the same equivalence class, that is, gamma tilde is another member of xp, then gamma tilde must share the same tangent with gamma, and therefore ddt of phi composite gamma of t at t equal to 0 must be the same as ddt of phi composite gamma tilde of t at t equal to 0. And then it should be pretty easy to check that these two numbers, the directional derivative whether you use the curve gamma or whether you use the curve gamma tilde, are exactly one and the same. So the directional derivative depends only on the equivalence class xp and not on the particular curve that you use from the equivalence class. So it's really a function of the equivalence class itself. Now, note that what the directional derivative actually is giving me is a number starting from a function. So it's a way to change a function to a number. And not only that, it's a way which changes a function to a number linearly. If you replace f by a linear combination of different functions, the result will obviously be a linear combination of the corresponding results. Using this, what we do is, corresponding to a germ xp, we define a linear map, which we are calling xip for the time being. There is a map which takes in a function, so an element of ckm, and puts out a number. And the way in which you define this is simple. You apply xip on the function f, and because this is a functional, something which eats a function and gives a number, I am using a square bracket. This is the notation that you have already seen before, and is defined to be the directional derivative of the function in the direction of any curve which represents the germ xp. So take any curve gamma from xp and calculate the directional derivative in its direction. Now this xip should be very familiar to all of you. This is exactly what we have been calling a tangent vector according to the algebraists definition. And this gives us a connection between xp and xip. Indeed, every xp defines a unique xip, and a moment's thought will tell you that given a xip, you can use it and figure out exactly the equivalence class xp to which xip corresponds. Indeed, we usually do not differentiate between xip and xp. I have only provisionally denoted this object xip. Usually what we would say is that the equivalence class of curves acts on a function in this linear fashion and provides a directional derivative. Now the properties of this map xip should be very, very familiar from what we have said about the algebraists definition for vectors. So I'm not going to elaborate on that any longer. But what this does show you is that corresponding to every equivalence class of curves, there is a linear functional, which is a derivative map. And just like we do not usually notationally distinguish between xip and xp, we actually use the same letter, xp, for both. Similarly, What we have been calling tau pm actually is indistinguishable from TPM. At the face of it, this may seem rather unusual because on the one hand, tau pm contains equivalence classes of curves, whereas TPM is a set of linear derivative maps. However, as you can see, there is a one-to-one correspondence between these two sets which preserves their basic structure, that is the vector space structure, which is why you can either use the linear functionals or use the equivalence class of curves picture and you get the same results no matter what you do. This brings our discussion on the various kinds of ways to define vectors to an end. Of course, we will have a lot more to say about vectors and vector fields in the coming lectures. And we will mostly stick with the algebraist definition because many results can be derived much more easily there. So let me call it a day for now, today.